Hello, grade 11s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabudiwa Sos Ugobela Wemet. And without any further ado, let's look at these questions that we have here. Okay, so we have question 2. It says 3-point charges, Q1, Q2, and Q3, carrying charges of positive 6 microcoulomb, negative 3 microcoulomb, and 5 microcoulomb respectively, are arranged in spaces shown in the diagram below. The distance between Q3 and Q1 is 30 centimeter, and that between Q3 and Q2 is 10 centimeter. So as we can see in the diagram here, then 2.1, it says state Coulomb's law in width. So that's the definition as we can see it here. The magnitude of the electrostatic force exerted by 2-point charges on each other is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. Right. Then we have 2.2. It says draw a force diagram showing the electrostatic forces exerted on Q3 by Q1 and Q2 respectively. So all you have to do there is indicate the dot to indicate your Q3 there, and then now let's draw the vector for our forces. So Q3 here is experiencing a force from Q1, but then since Q3 is positive and also Q1 is positive, we know that the force that will exist between these two charges will be a repulsive force. So where will Q3 go in terms of Q1? Obviously, Q3 will be repelled to the left-hand side. So we need to indicate this is the force of Q3 due to Q1. Right. So we're saying that Q3 will be repelled to the left due to the repulsion force it feels from Q1. But then what about Q3 here? Q3 is a negative charge. Q2 is a negative charge, while our Q3 there is a positive charge, right? So that means the Q3 will be attracted towards Q2 because remember, unlike charges attract, right? So there we go. So our force diagram will just look like that. And then this one is force of Q3 due to Q2. So that's all you should indicate for 2 marks. So let's indicate this is for 2.2. Then 2.3 says calculate the net force exerted on Q3 by Q1 and Q2 respectively. Right. And then that is for 8 marks. So we talked about this question here. This simply means that you should first calculate the electrostatic force that exists between Q3 and Q1, and also the one that exists between Q2 and Q3. Then from there on, you're going to use your Pythagoras theorem to find your net force, since this is a 2-dimension question. So it is still the same way as you would approach the vectors in 2D if you had vectors in 2D. So nothing changes, just that now you have forces. So let's go now for 2.3. Let's start with f of Q3 due to Q1, right? So our formula is F is equals to K Q, let's just edit it to say Q1 and then multiplied by Q3 over R squared. Now our K, we know it's always 9 times 10 to the exponent of 9. That's a constant. Then what is our value for Q1? That's 6 times 10 to the exponent of negative 6. Remember, microcoulomb, when we convert microcoulomb, we say multiplied by 10 to the exponent of 6. Right. And then what is our value for Q3? We have 5 times 10 to the exponent of negative 6. But then look at this. We are given our distance in terms of centimeters. So what is it that we should do first? We should say 30 centimeters divided by 100 so that we convert this distance here into meters, right? So if we divide that one, we say 30 divided by that, it's going to give us 0.3, right? So we want to substitute it here. And then we have our 0.3 and then square. Now we have to punch all that into our calculator. So if we punch that in our calculator, we get 3 newtons. and then to which direction. Remember, according to our force diagram, this was going to the left, so we need to indicate here left, right? So okay, we are done calculating that one. So let's now calculate F of Q3 due to Q2, right? And then that, so we have F again is equals to KQ, let's say Q2 multiplied by Q3 over R squared, right? Then our K still 9 times 10 to the exponent of 9. Our Q2, however, is 3 times 10 to the exponent of negative 6. Remember what we talked about. You do not substitute the negative into this formula there, right? And then the other one, the Q3, is supposed to be 5 times 10 to the exponent of negative 6 once again. But then the distance in between, this time we're given 10 centimeter. So what do we do? 10 divided by 100. This will give us 0.1 meters. So we want to include it here, 0.1 square, right? Then when we punch all that into our calculator, let's quickly punch that. We have 13.5 newtons. But then remember, according to our force diagram, this was going downwards, right? So we need to indicate this is downwards. Now, we are left with calculating the net force. So how do we calculate the net force right now? We should use this formula here from the Pythagoras theorem to say that we have F net will be equals to, so if we term this F1 and then we term this F2, this is the same as F net squared will be equals to square root of F1 square plus F2 square, right? Then what is our F1? That's 3 newtons, but then it's going to the left. So if we are taking right as positive, that means left is negative. So we can indicate it as negative 3 square. This one here, it's going downward. If we are taking upward as positive, we can indicate this as a negative. Then this is negative 13.5 and then square. Now, all you have to do is punch all this into your calculator, and then you will have 13.83 newtons, right? But then remember, right now you cannot say up, down, left, or right, because what you have here is the hypotenuse. So in order to find the direction of the net force now, we have to use the trig ratio tan, right? So to find the distance now, we say tan theta is equals to, remember the F2 represents the vertical, so we'll say F2 over Fy. So it must always be the vertical one divided by the horizontal one. So remember, this was F1, it was horizontal, and then this is F2, it was vertical. So it's always the vertical force versus the horizontal force divided by the horizontal force. Then now to calculate our angle, then our F2, remember we had 13.5 and then over 3. And then let's calculate the theta now. The theta is equals to 77.47 degrees. So that means, in other words, this is our F net. This is our F net. Let me fix here. If we already have the square root here, we must get rid of this square here. My mistake. Okay, so we have F net is equals to square root of F1 square plus F2 square. Then our F net is 13.83 newtons in the direction of 77.47 degrees, right? So that's our F net, 13.83 newton in the direction of 77.7 degrees Newton from the x-axis, right? So, okay, that's how you were supposed to tackle that question for 8 marks. Then you hinted on the fact that I should show you the mark allocation. So this is how you'd be marked for that one. So for the formula here, they will give you a mark. And then for substituting here, a mark. And then correctly substituting your distance is a mark. And then now, that's already 3 marks there. and then you go to this formula here. Because they already gave you a mark for the formula, they won't give you again. So they will mark here and they will mark there, right? And then from there, they will give you a mark for finding your F net, substituting this here. So, and then also a mark for finding your angle there. And then a mark for the conclusion on the F net, right? So if we count all that, that's 1, 2, 3, 4, 5, 6, 7, 8. So that's how your marks will be allocated there. Okay, so now let's move to point 4. Two identical spheres A and B carrying charges of positive 5 nanocoulombs. Note this, we are now given in nanocoulombs. So we already know nanocoulombs. We're going to convert it by saying times 10 to the exponent of -9. Then two identical spheres, A and B, carrying charges 5 nanocoulomb and -10 nanocoulombs. So note that they are just identical spheres, but then they do not carry the same amount of charge, right? Are separated by a distance of 30 millimeter. Now again, the distance is given in millimeters, so we know that we have to divide from millimeters to meters. We have to divide by 1000. So it is very crucial that you note the necessary conversions that you will need just before you even start answering the question. Then are separated by a distance 30 millimeter. P is a point located at a distance of 15 millimeter from sphere B as shown below. Then we are given that. So this is a point charge here. We already know that they're going to ask us questions on the electric field if they ever give us the point charge. Then the spheres A and B are allowed to touch each other and then return to their original positions. So they're allowed to touch each other and return to their original positions. Then 2.4.1 says define electric field strength at a point in which. So there is the definition there. It says the electric field strength at a point is the electrostatic force experienced per unit positive charge placed at that point. Right. So that's how you define it for 2 marks according to your CAPS document. Then 2.4.2 says draw an electric field pattern between sphere A and B after touching. Note this, after touching. Right. So before they touch, we understand that they are attracting. They have an unlike charges, so they will attract. But then remember, after they touch, they will separate to their original positions, mainly because after touching, they share the same magnitude of charges, and also they have the same direction on the charges, right? So that means after, note this, if they say after touching, that means right now you have to draw the one whereby they repel, right? But then right now, will it be a positive repulsion or negative repulsion? Based on the fact that we can see that our -10 here is the bigger number, we know that if we do our Q new, so for 2.4.2, if we were to say Q new, then this would be positive 5 plus -10, and then divided by 2, which will give us something like -2.5, right? So this one is negative, as we can see. That means all the charges, charge A will now have -2.5 nanocoulombs, and charge B will also have -2.5 nanocoulombs. So this is the reason why they separate. They separate because they now have the same magnitude. They now separate because they have the same sign on the charges. Remember, like charges, they do what? They repel. So this is a negative, this is a negative. Hence, they repel and then they go back to their original positions. So the electric field that we should draw here, note, is the one whereby we say this is a negative, and then also that one is a negative, right? So always be careful when they say after touching. So we go like that, like this, ta. So you don't have to draw a lot of fill lines, guys. You don't have to. It is not necessary that you draw a lot of fill lines, because remember, the more fill lines that you draw, you risk you risk the fact that they might end up crossing or touching each other, which if they ever touch or cross each other, then you don't get your mark, because the marking criteria says the fill line should not touch and they should come from their own individual point. Now, we know that if these are both negative charges, then we should see our charges here being inward. Remember, on a negative charge, the charges, we say they are inward. So you show your arrows going inside that charge there. So there you go. So this is all that you're supposed to indicate. Then this is how many marks? This is 3 marks. So the marking criteria or the marking guideline says you get a mark for the correct shape. So you get a mark for the correct shape. And then you get a mark for correct direction of fill lines, correct direction of fill lines. So there's a mark there. If you have indicated that the fill lines are going inward because it's a negative, and then also you get a mark if no fill lines ever cross, no fill lines crossing. So they should not cross, they should not touch. Then you get a mark. So now you know where you get your marks. So the fill lines do not touch, the correct direction of the fill lines, and then you have the correct shape. Okay, so that's how you were supposed to get that 3 mark. Then 2.4.3 says which sphere has an excess of protons before their contact. Note, excess of protons, not electrons. Excess of protons. So the one with an excess of protons, we do understand that it is the positive one. So it is definitely A. So charge A is the one with an excess of protons. Now 2.4.4 is saying calculate the new charge. So we already tried to calculate that one, but now let's just calculate it correctly. This is Q new is equals to Q1 plus Q2 over 2. Remember, when we calculate, we must convert that nanocoulomb. So that's 5 times 10 to the exponent of -9 plus -10 times 10 to the exponent of -9. Note that in this formula from grade 10, you can substitute a negative value. But then once you get to the formulas from grade 11, which is the one to calculate electrostatic force and the one to calculate electric field, then you don't put a negative there. But on these ones here, you can put a negative. Now your Q new is equals to what? -2.5 times 10 to the exponent of -9 coulombs, right? So do not forget the SI unit there. And then how many marks was that? It was 3 marks. So they mark the formula. So they mark the formula, they mark the substitution, they mark the correct answer along with the SI unit. Remember, I told you if you do not include that SI unit there, then you definitely won't get that mark. Okay, so now we go to 2.4.5. It says calculate the magnitude of the net electric field at point P due to A and B. Due to A and B. Okay, so now to calculate 2.4.5, let's do this. Note that question here, there's always this trend. If they ever ask you that question right after you have calculated the new charge, that means you can no longer use these values here. Note that. So the mistake that a lot of you usually make when it comes to calculating that net electric field, you still move along with these charges here. But then that is incorrect, guys. Remember, you have now calculated the new charge. These spheres were allowed to touch each other and then return to their original positions. That means the old charges no longer apply. We are now going to roll with the new charges. So this is -2.5 times 10 to the exponent of -9, and also B is -2.5 times 10 to the exponent of -9 coulombs, right? So this is the new charge that we are going to use now. So the distances are still the same because remember they said they are returned to their original positions, right? But then now being returned to their original positions doesn't mean they still carry the same charges. Remember, now there was a distribution of those charges, right? So that means we now use the new charge. Note that that question is coming right after 2.4.4, which was saying calculate the new charge. So how am I supposed to calculate that one? When I say, okay, if I want to calculate the one from, I'm trying to calculate the electric field from of P, so electric field of P due to A, then we know that the electric field here, I mean, the point charge is always positive, but then if the point charge is positive and A here is negative, that means the point charge will be attracted towards A. So that means indicating the force diagram or the free body diagram, this would be what happens. So this would be the electrostatic field, the electric field of P due to A, since now it will be attracted towards that. And then again, the B is negative as well. So that means the point charge has to be attracted towards B. So obviously B, because the distance is shorter, will produce a greater electric field. So EP due to B. So now we can say that the electric field on P will be going to the same direction, which is left, because it is being attracted to that side by both of these charges. Right. So now let's calculate. We have E is equals to K Q over R squared. Remember here with the point charge, we don't have any value. We are just supposed to substitute the values of the charges. Then K is 9 times 10 to the exponent of 9. Our Q there is going to be QA. So which is, I'm going to substitute what? 2.5. Remember, we do not substitute in that negative. Again, this is a grade 11 formula. The negative does not go in there. Now, what is my distance R? From A to P, note that the distance now is what? 30 plus 15, which is what? 45 millimeter. But then we should take this 45 divided by 1,000, right? And then now it's going to give us what? So let's write it like this. So it's going to give us 0.045 and then square that. Now, all we have to do right now is punch all this into our calculator. So it will give us 11,101.11 Newton per Coulomb. And to which direction now? We can see that it is being attracted towards that point. So it needs to be going to the left. Right. Okay, so now let's calculate E of P due to B now, due to B. So again, our formula E is equals to K QB over R squared. Our K, still 9 times 10 to the exponent of 9. But what is our QB? Again, it is 2.5 times 10 to the exponent of negative 9. Note that I'm using the new charges. So these ones are no longer applicable. Then what is the distance now between B to P? So we have that 15, and then we know very well that we should say 15 divided by what? 1,000. So this gives us 0.015 and then square. Now when we punch all that into our calculator, we get 100,000. So that's 100,000 Newton per Coulomb. And to which direction? It is going to the left as well, right? So it is going to the left. And then now, how are we supposed to calculate then? To calculate the magnitude of the net electric field at point P due to A and B, we should then say here, we should then say our E net is equals to E1 plus E2, right? So if we take this one as E1, then this one is E2. That means we must say 11,111.11 plus 100,000, right? So let's add that together. We have 100,000 11,000 plus 11,111.11. Then this should give us 3.1, and then 0.11 Newton per Coulomb. To which direction? Left, right, left. So we can also indicate that by saying negative and negative, but then if we are taking left as the positive direction, then that is definitely correct. So let's just take left as the positive direction so that we do not have to indicate a negative there. And then that's a 111,111.11 Newton per Coulomb to the left, right? Okay, so now 2.4.6, it says, if electron is placed at point P, calculate the magnitude of the force experienced by an electron. Right. Now, this is when you get to use this formula here. There is a particular formula where we get the definition of the electric field. Once they mention anything about an electron, this is the formula that we now use, where the Q here, the Q is the same as the QE, which is the charge on electron. So you substitute the charge on electron. This is always a constant, and then the constant there is given as what? Is given as negative 1.6 times 10 to the exponent of negative 9. Right. So we are to calculate the force. Remember, if electron is placed at point P, calculate the magnitude of the force. Now, our electric field is the one that we calculated, 111.11 is equals to F. Then here we should substitute this one here, which is a negative 1.6 times 10 to the exponent of negative 19. Right. And then if this one, remember this one, we said it's going to the left. And then if we say negative here, then this is F is equals to, if we say negative multiplied by negative, that's a positive. So let's go multiplied by 1.6 times 10 to the exponent of negative 19. Let's go. Now we will have 1.78 rounded off to 2 decimal places times 10 to the exponent of negative 14 newtons. Right. Remember, this one I indicated it as a negative because it's to the left. And then whenever I'm calculating my force, I just want it to be positive like that. So, okay. So this is the force that I end up having. And then for 3 marks, this is how they will mark that formula. And then a substitution into the formula. And then the correct answer there. And then that's how you are supposed to tackle this question here. Please press that thumbs up button if you have enjoyed the lesson and then you have found it helpful. And if you've been watching the videos and haven't subscribed yet, please hit that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.